Hello. Here I am explaining the formulas about simple stress and strain. This is module number 1. Okay. So first formula will be stress is equal to P upon F. Okay. Where will be stress is sigma denoted as sigma. P will be load applied and A will be a cross section area. Okay. Here when we applying a force on a cylindrical bar or any material. Okay. We are here applying a tensile force, right? This force magnitude is known as P. Okay. Then area will be a exactly perpendicular area of that force. Okay. Normal normal area, normal to that force. Always be taken as a normal. Okay. In a stress formula, means if consider a rectangular bar. Uh, Here it will be a compressive force, right? If we have to calculate sigma, then P upon this area we have to take. Then if we calculate, here will be another force F, right? Then for the sigma formula we have to take this F upon this area, right? Okay, that's all. Means always have to take perpendicular area, normal area to that force. Next formula will be a strain. Strain is delta L upon L. Delta L means change in length and L will be original length. Okay. When this bar is subjected to some force P, then length of that bar having some extension after applying that load, right? Having some extension. This extension is called delta L, means change in length. And so, but take the example, if we have a 10-meter bar, right? But we got after the applying of force, it goes like 10.005 meter. Okay, it expands up to 10.005. Then delta L value will be 0.005, right? If this will be subjected to compression force, this bar is subjected to compression force, compressive load. Okay, then what will happen? This original length will be contract, right? So if we calculate that length after applying of force, it will be 9.995 meter. Then what will be a delta L? Delta L will be a 10 minus 9.995. It will be 0.005, right? Meter. So this both delta L are same, but here is a hello. Okay, this will hello. If it will be contract, then we have to take a negative sign for that change in length. Okay, change in dimension. Okay, next will be a Hooke's law. Within elastic limit, the stress is directly proportional to strain. Okay, this sentence is very important in the whole strength of material subject or the whole syllabus. Okay, because we need to stay within an elastic limit for any formula or any formulation or any calculation. Okay, because within elastic limit, if delta L will be means change in length will be a 0.005, then it should be regain its original length after removing that load. Okay, after removing that load, if it goes beyond elastic limit, means it will expand up to 10.00, 10, 10.010, and after releasing load, its length will be 10.002. So it remains change, right? So here the formula will this formula will not work. Okay, means 0.010 divided by if original length we have taken as 10, then it will not be a strain. Okay, the strain is only considered if the delta L will be regain its original length after removing a load. In every formula you have to regain its original shape or size after removing load, then only all the formulas will work. Okay, so here is a elastic uh, young modulus. Okay, modulus of elasticity is a constant of any material. The E will be a constant of any material. Means every material has a different E value, like it's like a property of that material. Means by taking an example, uh, okay, means every human being has a different property, like means someone a person has a 65 kg weight, B person has a 70 kg weight. Okay, like the every material has a different E values which is always constant. Okay, it is always constant. And E, like we have like G for shear modulus, it's a sharing constant. K will be a bulk modulus, it will be a bulk modulus. This is, these are the constants for that particular material. Okay. This constant is at any point stress is directly proportional to strain. Okay. So stress. Okay. Next formula will be delta L. This formula is most important formula because many of problems comes with on this formula. Okay. Delta L is equal to PL upon A. Next, P is load, L, A, and E. Okay. All should be keep in within mm. Okay. Next will be a factor of safety. Suppose one material has its limit of taking stress is 100 Newton per mm square. 100 Newton per mm square. And if we design by taking this stress limit, it's a maximum stress, right? But at uncertain condition, and any uncertain condition, if load is increased slightly, then stress will be goes beyond 100, right? It will be 110 or 120. Uh, uh, as we know, it's a maximum stress limit is 100 Newton per mm square. Then it will be break easily with any uncertain load. Okay. So we have to take a factor of safety for that. Okay, means we have to design a particular product by taking this material. Then stress value we have to reduce by some percentage. Since we have to design it by taking 60 Newton per mm square, for example. Okay, so ratio of that both stress is called a factor of safety. Ultimate stress will be 100 and working stress is on the which stress we are working, this will be a 60 Newton per mm square. Then uh, if we are designing any product with that working stress, then if any uncertainty happens and the load increase by some for some time or for some value, then load increase will cause stress will be also increase. Okay, so it will go up to 70 or 75 Newton per annum. Okay. But it stays within its maximum limit, right? So it won't break uh, at any smallest users users mistake. Okay, so okay, so it's called a durable product. Okay, next will be elongation due to self. So suppose some the material is hang, there is no load applied on it. Okay, hang, but due to its self weight, it also elongate by some distance. Okay, elongate by some distance. This elongation we can calculate by this product. Delta L is equal to W L upon A. W will be a self weight and L will be a length of original length, and area is also this area, and E will be W. We can calculate by density, omega gamma density. Okay, density into volume. Volume will be area, this area into length. Okay, that's all. Density into volume will be a weight. Okay. Next formula, modulus of rigidity. Okay, as we know, this will be a rectangular bar and load is applied here, F. Then for the stress, what are we taking? F upon A. But area where we taking was this, right? For the tensile or compressive load. But at a sharing load, what will happen? We are taking this area for that formula, but here we are not taking the stress. Here we are calculating the shear stress. Okay, shear stress. For a shear stress, there will be F upon this area. Okay, here this area. Okay. So it will be calculated for sharing. Okay. Not taking a normal area or perpendicular area for a sharing calculation. Okay. Then G is the shear modulus. In that, shear stress, you know, F upon A, and shear strength will be theta. Okay. So next, Poisson's ratio. Poisson's ratio also property of material. Its property means it's constant, right? Like person has a weight or anything. As same, it's a property. Poisson's ratio is denoted as mu, which is also we know we denote as 1 upon m. Okay, this you can see in any example the 1 upon n is equal to something 0.3 etc. Okay, so 1 upon m you have to take as a mu or Poisson's ratio. Okay, Poisson's ratio is negative of lateral strain upon longitudinal strain. Okay. Lateral strain will be delta d upon d. Okay, lateral means, you know, this is length, right? In a certain condition means if we are applying a tensile load on this, then P upon this area, okay, certain load, then length will be increased, right? But other two width and height will be decreased, right? Will be decreased. Same for a circular bar. If the length will be increased, then diameter for that bar will be decreased, right? If length is increased, diameter will be decreased. So diameter has also some change in diameter. It's known as delta D, right? Delta D upon D, original diameter, is known as lateral strain. Okay. But delta D value, if it's contract, okay, contract, then delta D value you can take negative of something, okay, and L value will be a positive. If it's in a compressive load, then delta D will be positive and delta L will be negative. Okay, so for merging this two strains, we need to change the sign. So here we are taking negative of lateral strain upon longitudinal strain. Okay, so negative and under negative, yeah, in our negative we will convert into positive. Okay, then we go to a volumetric strain, delta V upon V. For the all resultant strains and resultant change in volume, yeah, we only see here a change in length, right? And here we are saying change in diameter. But by combining this, the whole volume will also be changed. It will be contract or expand. Okay. So this all change in volume will be a volumetric strain, known as volumetric strain. Then for circular rod, EV is equal to 2 ED plus EL. ED means as we discuss right now, delta D on D means change in diameter on original diameter plus EL. EL means delta L upon L. Okay, but 2 times ED plus EL. Next, volume, as we know, of a circular rod, pi by 4D square into L. Okay. Then for rectangular ball, volumetric strain will be EB plus EL plus ET. And so for width, thickness, and length strain. Then for bulk modulus, K is equal to sigma upon EV, right? K will be a bulk modulus. Sigma is equal to stress. EV is a volumetric strain. Relation between EC and K will be E is equal to 3K 1 minus 2 mu. E is equal to 2G 1 plus mu. Means E is here strain modulus of elasticity. K is bulk modulus. Mu is Poisson's ratio. G will be shear modulus. Here KC, C is also known as shear modulus. C and G both are same. Okay, that's all.